for our system. And we needed a configurable approach, so we went with a hybrid between a behavioral and a goal-based robotic architecture. You see it coming up from the top. The sensor data comes in to the core, which the core is controlled by a finite state machine on the right. That basically tells the core which behaviors are on in the current state, and the core then forwards the sensor data down to the behaviors, and the behaviors outputs are summed through the arbitrator, and that output is sent down to the wheels. And this allowed for us to keep some of the modularity and ability for behavior-based and still keep an overall goal. All right, our actual implementation of this was in Linux. We used a multi-threaded event-based architecture where we had several threads listening for our communications. Communications occurred. We passed them off to message processing threads, which validate the data and turn it into an event that gets handled by our event processing thread, which calls all the behaviors and sums up their outputs. One of the great things about this architecture is it's expandable. One of the things that we have is IP communication. We can expand and add additional behaviors in any programming language that can communicate via sockets. We have that capability in there. And it also, the finite state machine that is controlled by comes in through a configuration file. So that is not, you don't require any code changes. And to actually help us do that, we created the RCA, which is our configuration GUI. Basically allows us to visually put out the finite state machine. If you can see here in the center, the red circles represent the states the robot's in, and the blue transitions between them. We basically can drag and drop with these and determine what transitions occur based on behavior outputs, and auto-generate that configuration file that gets passed into the robot. So no code change, and you can totally change what the functionality of the robot is. In addition, new behaviors their code can be auto-generated. So you just specify, the language, specify what sensors they are triggered by, and the code will automatically be generated, linked into the system, and activated and called. Now we're going to show you a little video about it. Just a note, on the video there is a cable going behind the robot. That cable is a power cable. We developed each one of our pieces individually. When we brought them all together, we just barely went over the current limit. So one of the devices had to be powered from a wall thing. It's not a communications. We're not controlling it.
No fair, you moved the box away at the end.
So on the administrative part, the total cost of our parts came up to be about $885. We'd like to note that after we removed some of the parts that we found out not working, the total project cost was significantly reduced to $498. Comparative solutions from GMU, such as a Flockbox system, cost about $800 for a similar solution with less sensor functionality. In terms of hours worked, we charged our time $25 an hour, and the total cost of the labor came out to be about $27,000, and the total cost of the project about $28,000. Now, on the administrative slide, one of the interesting things that our group did is that we kind of had a difficulty because we're not all working in the same cubicle, in the same office. So what we did is we created a wiki. And what this wiki allowed us to do is it allowed us to do our own little parts and then post this online. And so other people who needed to use our code or some kind of functionality, because all the functionality is built on each other, would simply go onto the wiki and look at our information. In addition, we used a subversion source control provided by Tortoise SVN to keep control of our code. Lessons learned. One of the most important lessons here, and if you guys are doing 492 now, do not neglect your power supply, especially on an embedded system. Power supply on an embedded system is never as good as a wall board. Some circuit components can get hot, especially voltage regulators. The simple solution is always the best solution. This was a very humbling realization for us. Seek advice and ideas from your faculty mentors and other faculty early. Have a plan B, C, and D. And as well, one of the most interesting things that I really should have looked at is that if we looked at the forums online, we would have figured out about some of the problems that some of the systems that we had before we bought them. It would have saved us a lot of money. We'd like to especially thanks to Asia, Dr. Luke, Randy, Keith, Brian, Dr. Beatty, the Luke family for letting us take over their basement, Bill Wadley, Amrik, and Brandon. Have any questions?